Hello everyone, and today we're looking at motion, reference and speed, and the subtitle for this is Basic Interactions with Time and Space. A slightly lofty title perhaps, but that's really accurate. These are the sort of things that you will do every day and you will never actually think about moving around in space and moving objects from one place to another. It's things that we take for granted, but the basic rules are what we're looking at here. So the first item on the title is motion, and we all understand what it means to be moving, but we're now going to clearly define motion. Something is in motion if it is changing position. And so this puts a clear definition on the idea of motion. It could be a fast-moving aeroplane in motion, it could be a leaf in the wind, it could be water running down a river, or anything else that's moving. But motion is when something is changing position. But of course that means that if we want to be able to measure motion, we need a way to accurately define position, and that's what frames of reference are all about. Before we get to frames of reference, however, we need to think about the idea of distance as well. So the place you are in now is actually moving. I can say that with confidence because you are somewhere on the spinning planet Earth moving through space. And that means that you are in motion. And so over time you will get further and further away from where you started. And so exactly how far you move is what we call your distance. And we're going to measure these quantities using SI units, which is something that you should have covered earlier in your high school course. And SI units, you may remember, is the system we use to make sure all our measurements are in line with each other and all the units are the same size. So let's just explore these ideas by taking a short walk. Well, Katie takes a short walk, to be precise. From her house, she walks 200 meters north, she turns right, and she walks 500 meters east. Then she turns right again, and she walks 400 meters south. Here she meets her friend Dan, and she stops to have a bit of a chat. Then she takes another right and goes 500 meters west. And finally she turns right and walks 200 meters north. So just like you to think about these questions. How far did Katie walk? How far is Katie from her house at the end of the walk? And how far was Katie from her house when she stopped to talk with her friend Dan? Have a think about those questions, pause the video if you need to, and we'll talk more about them on the next slide. So now we need to discuss the difference between distance and displacement. Distance tells us how far you move, but it actually says nothing about exactly where you move. Displacement, on the other hand, is a measure of how far you are from your specific starting point. And that means it will include the direction that you moved from your starting point. So what this means is that distance is a scalar quantity and displacement is a vector quantity. And we will define those words on the next slide. But first, let's look at a diagram. This is Katie's walk from the last slide. And you can see there that she walked 200 meters north, 500 meters east, 400 meters south, then she talked to Dan, went 500 meters west, and then finally 200 meters north. And so at the end of her walk, she was 0 meters from her house. She walked all the way around the block and she arrived back at her house. However, when she stopped to talk to Dan, she was actually 538.5 meters from her house. If Katie's mum at that time had wanted to send Katie her lunch by drone, she cannot only know that Katie is 538.5 meters away, she must also know what direction she needs to send the drone in order for it to reach Katie at the end of that 538.5 meters. So in order for her to do that, she needs to know not just the distance, but also the direction. So as promised, we're going to define vector and scalar quantities. Although you might already be getting a feel for them, they are two very common types of quantity that you find in physics. Scalar quantities have only a magnitude, they have only a size, whereas a vector quantity has a magnitude and a direction. So for example, the weight has a mass of 1,000 kilograms. That is a scalar quantity. The weight has a force of 1,000 newtons. That is a vector quantity. They look very similar, but the second sentence isn't fully clear unless we know what direction the force is acting in. For the first sentence, we know that this big metal object has a mass of 1,000 kilograms, and that's all we need. That is a complete statement. However, the weight has a force of 1,000 newtons. We have no idea what that force is going to do if we don't know what direction the weight is actually going. So when you're doing physics, you need to look at things in many different ways. We've already talked about this actually. So you, wherever you are probably sitting down right now, and that means that you are not moving relative to the chair you are sitting in. But what if you are sitting in a car that is driving along? In that case, your chair is in a moving car. As we said before, that chair is definitely on the rotating Earth, and so over time the Earth rotates around and moves in space, and the Earth is orbiting the Sun, which means that you are not only rotating on the planet, but the planet itself is moving around the Sun. So in one way you are not moving relative to the chair and maybe the building around you, but in many other ways you are actually moving. And all these different ways of looking at physical movement in space are called different frames of reference. So what is a frame of reference? Well, imagine we have an object in space. It's important to note that this could be an infinite space. There's no limit to the size of the space. But to make things easier for us, let's just limit our object into this box of space. And inside the box, we can use coordinates to define exactly where in the box the object is. And once we can do that, we have a way to accurately say what the position is. Remember, that was an important thing we needed for defining motion. And so once we have this system, we can use our understanding of physics to construct a model of the object movement. So that means we have a single reference frame, and that is a single coordinate system based around a single stationary origin, at least stationary with regard to this object. But what if we have another box, another reference frame? This reference frame could be moving. It could be in a car driving down the road or in a spaceship flying through space. So the same rules will apply, but we have to take into account the fact that the reference frame itself is moving. And so some of the biggest problems of the physics of motion are about how we can relate the movement of two objects in two different frames of reference under one set of equations. So let's try and simplify that as quickly as we can. A frame of reference then is a consistent system of points that we can use for measurements. And our reference point is the origin of that system. It is the 0, 0, 0 point if you're in 3 dimensions. And we take that to be stationary, at least within that reference frame. And then your displacement is your distance and direction from the reference point in that frame of reference. But remember, there are other frames of reference, they have their own origins, and they could be moving with respect to your frame of reference. But we want to keep it simple. The good news is, in this course, we're only going to be taking objects in the same frame of reference, so you never have to worry about combining different reference frames. But many modern scientists do need to do that, and they need to work with the equations of relativity in order to do so. If you want to work with objects in frames that are moving constantly, then you need special relativity. And if you want to work with accelerating reference frames, then that means you need general relativity, which is incredibly complicated. And you may have heard of relativity. It is the great discovery that made Einstein into a scientific megastar. It was his first great and arguably biggest ever contribution to the understanding of science in the 20th century. So we've been talking a lot about movement. It's about time we brought up the issue of speed. And speed is a concept which you probably know well from everyday life. But again, what is it all about in physics? Well, it is actually one of the most intuitive relationships in physics. It's really quite easy to understand in a physical way. So you should make sure that you understand this very well, because as physics gets more difficult and more abstract, it is harder and harder to relate the equations you see to the real world. So speed is a good introduction to that kind of process. So what happens? If you move a certain distance, which we measure in meters, the SI unit of distance, and it takes a certain time, which we would measure in seconds, then you are going to travel x meters every 1 second. And so we call x your speed, and we find it by dividing the whole distance over the time that you took to travel it. So the overall distance traveled divided by the time taken to travel it. And what this gives us is the distance traveled per unit of time. So the distance traveled per unit of time, and the unit of time is seconds, so you travel x meters in every 1 second. It's important to remember though that we are averaging the speed. So you could travel a certain distance in a certain time, but you could change your speed. You could start off very, very slow and you could end up very, very fast. So what we are calculating when we calculate distance over time is the average speed that you traveled over the course of the whole time and the whole distance. So a little bit more on the speed equation. Speed is, as we said, a measure of distance traveled over time, and it is a scalar quantity. We represent it as symbols, and we use the symbol v to represent speed. We'll talk about why in a minute. D is distance, and then T is time. And we've put on the left-hand side there all of the different symbols we are using and the units that they are representing in the equation. And you can see there that the unit of speed is the meter per second, m/s. And if you look at the equation, you'll see that we are actually dividing the number of meters by a number of seconds. So the unit actually shows how the equation works. And just as a quick reminder, this equation can of course go into one of the magic triangles of physics, allowing you to easily remember how this equation works and the relationship of the symbols to each other. So you need to be careful when you're dealing with some equations, because unfortunately different systems of writing equations still exist. So distance is given the symbol d, but displacement uses the symbol s. Unfortunately, speed also sometimes is written as s, and v, as we saw in the last slide, stands for velocity. Velocity and speed are very similar, but there is a difference which we will see in a few slides' time. But this shows why it's important to keep track of your symbols, because some places you might think S stands for displacement, and in actual fact it stands for speed. So let's just have a quick look at some speed problems using that equation. So a runner runs 100 meters and finishes that race in 11.4 seconds. What was their speed? Try and work it out for yourself. Or what about a passenger train? Travels a distance of 250 kilometers in 3.5 hours. A man drives his car 300 kilometers in 4.5 hours. Which one travels faster? And there it also says give the speed of both in meters per second. So there you have to do two calculations to find out which one has the faster speed, but also you have to give the speed in meters per second. If you notice, the question is in kilometers and hours. So a little bit of unit conversion is going to be necessary to answer those problems. So I'll let you think about those on your own, and we're going to move on to the next slide. And you can actually plot a relationship between the distance traveled and time taken on a graph. It's called a distance time graph, imaginatively, and all it is a simple set of axes with time in seconds along the x-axis, the horizontal axis, and distance in meters up the y-axis, the vertical axis. And then you just plot a set of points so that after 1 second their distance traveled by the object is a certain value, and after 4 seconds the distance traveled is another certain value. And in this way you can also work out the speed. How would you do that? Well, if we look at this object that's moving, this blue line, we can see that after 1 second the object has traveled 4 meters. And then after 2 seconds the object has traveled 8 meters. And then after 3 seconds the object has traveled 12 meters. After 4 seconds the object has traveled 16 meters, and then you can also see after 5 seconds it's traveled 20 meters. So every second this object is traveling 4 meters. So it has a speed of 4 meters per second. And this also is shown by the fact that the line is straight. The straight line shows that the speed is constant, that the distance traveled is going up the same amount with every unit of time taken. And what this tells us then by simple maths is that the slope of this graph is in fact the speed of the object. So we have here a delta y over delta x equation, and you may have seen this in maths class for the gradient of a graph, the change in y over the change in x. But remember, on this graph x is the time taken and y is the distance traveled. So that means the gradient is the change in distance divided by the change in time, which is exactly the same as our speed equation. So the gradient of a distance time graph is the speed of the object. If the line is straight, the speed is constant. And if it's not straight, then, well, it gets more complicated, and we won't be looking at that today. Let's just have a look at another example, though. This isn't quite as simple. You can see it is going up straight. It's the same amount every time, and you can probably read off the change after every second if you try, but it's not going an exact number of meters. But that's okay. All we need is 1 point which we can easily judge. This one looks nice and easy. After 4 seconds, the object had traveled 10 meters. And then we can just use our speed equation. We can divide 10 meters over 4 seconds to get 2.5 meters per second as the speed of the object, shown on the red line. And we're going to finish off by talking about velocity. Velocity is very similar to speed, as we said, but it also includes the direction of the motion. That's the difference. And so therefore, velocity is a vector quantity. Vector quantities can be broken down into different components. And here we're going to see frames of reference in action again. So take a look at that vector on the left there. You've got 7 meters per second and a direction. So what are the components of this vector? Well, it does actually depend on what the frame of reference is. So first of all, you would choose a frame of reference. Let's choose a fairly simple one, shall we? We're going to put a simple set of axes over this vector, and just for ease, we're going to put the origin at the start of the vector. So we've chosen to put the origin of our frame of reference at one end of the vector, and we can now think about that vector within the frame of reference. And what might be jumping out at you now is that we can create a right-angled triangle around the angle between the vector and the x-axis. Now we have a right-angled triangle and we have a vector with a magnitude of 7 as its hypotenuse. Using simple trigonometry at this point, we can break down the vector into components in this frame of reference. So, with the information we have and the frame of reference we've chosen, we can tell that this vector has a component of 6.1 meters per second eastwards and 3.4 meters per second northwards. And that's where we're going to leave it in our little talk of motion and reference frames. We've covered most of the major concepts, perhaps a few more than we needed to, but it is important that you realize that when you're discussing frames of reference, things can get very quickly more complicated than you think if you don't keep careful track of all your unknowns. See you next time.